Category O, Lecture 30, Koszul miscellanea. Let us start by recalling the Koszul duality theorem. Let K be an algebraically closed field and A a positively graded K algebra. So it is a direct sum of homogeneous components indexed by non-negative integers. So here the zero component is semi-simple and all components are finite dimensional. Let A shriek denote the quadratic dual of A, and A FG mod the category of locally finite dimensional graded A modules. Recall that a positively graded algebra A is called Koszul, provided that all graded simple A modules concentrated in degree 0 have linear projective resolutions. And here is the Koszul duality theorem due to Beilinson, Ginzburg, and Zergel. So if A is Koszul, then there is an equivalence K of the down arrow derived category for A FG mod to the up arrow derived category of A shriek FG mod, which intertwines the homological shift and the shift of gradient in this non-trivial way, which sends simple A modules to injective A shriek modules, and which sends projective A modules to simple A shriek modules. Now let us recall the application of the Koszul duality to category O. Let G be a semi-simple finite-dimensional complex Lie algebra with a fixed triangular decomposition into the negative part and minus, the Cartan subalgebra H, and the positive part and plus. Let W be the Weil group of G, and O the associated Bernstein-Gelfand category. Let O0 be the principal block of O, and let A be the basic algebra of O0. Theorem, due to Zergel, the algebra A is Koszul, moreover it is Koszul self-dual. In other words, A shriek is isomorphic to A. Koszul self-duality of O0 induces a non-trivial transformation on the isoclasses of simple modules. So in particular, it sends the simple module LW to the indecomposable injective module I, W inverse W0. Additionally, we have seen that all Verma modules in O0 have linear projective resolutions. That is, they are Koszul modules. Now let us discuss linear complexes of projective modules in connection to centralizer subalgebras. Let A be a positively graded algebra, and LCP the category of linear complexes of projective A modules. We know that this category is equivalent to A shriek FG mod. Let E be an idempotent in A0. Then the algebra EAE is naturally positively graded. It inherits the structure from A. Let P upper E be the analog of the projective generator P, but for the algebra EAE. And consider the category of linear complexes of projective EAE modules, LCP upper E. So similarly to the above, this category is equivalent to the category EAE shriek FG mod. We also know that the category LCPE is the Serre subcategory of LCP generated by PE. So PE is a semi-simple object of the category LCP, and of course by all its graded shifts. So in other words, linear complexes for centralized subalgebras correspond to Serre subcategories of the original category of linear complexes. Now we can discuss the setup for the parabolic-singular Koszul duality. So let P be a parabolic subalgebra of G containing the Borel subalgebra H plus n plus. Consider the corresponding parabolic category OP, and let WP be the corresponding parabolic subgroup of W. Let short WPW denote the set of all shortest coset representatives of W modulo WP acting on the left. Then we know that the principal block O0P is the Serre subcategory of O0 generated by all simples indexed by such shortest coset representatives. We can also consider the set of longest coset representatives of W modulo WP acting on the right now. So let lambda p be a dominant integral weight with singularity WP. And then we can consider the corresponding singular block O lambda p of category O. And we know that simples in the singular block are exactly the translations to the WP wall of the simples in the regular block, which are indexed by the longest coset representatives of W modulo WP. Now we are ready to formulate the parabolic singular Koszul duality. So let AP be the algebra of the singular block, and let A upper P be the algebra of the parabolic block corresponding to P. Theorem by Beilinson, Ginzburg, and Zergel. Both algebras A sub P and A upper P are Koszul. Moreover, they are Koszul dual to each other. Remark: conceptually, it would be more correct to use P prime for one of these algebras, where P prime is a parabolic category defined such that WP prime is the conjugation of WP by W0. However, we know that the conjugation by W0 corresponds to an automorphism of the Dynkin diagram, and therefore the corresponding algebras A lower p and A lower p prime are isomorphic, and similarly A upper p and A upper p prime are also isomorphic. Let us sketch the proof of this parabolic singular Koszul duality. We have the indecomposable projective functor theta 0, lambda p from O0 to O lambda p, and this functor sends simples to simples or 0. By adjunction, the adjoint, which is the projective functor theta lambda p, W0 p dot 0, from O lambda p to O0, must send indecomposable projectives to indecomposable projectives. So recall that A denotes the algebra of O0. Let E be the idempotent of A corresponding to the longest coset representatives in W modulo WP acting on the right. Then this projective functor theta lambda p, W0 p dot 0, it gives rise to an algebra monomorphism from the singular algebra A lower p to the centralizer subalgebra EAE. One can check that the image of this monomorphism actually coincides with the subalgebra of the centralizer subalgebra EAE, which is generated by the degree 0 and the degree 1 part. And it's a little bit more difficult to show, but one can show that this image is in fact quadratic. By looking at the linear complexes of projective modules over the centralizer subalgebra, we see that the quadratic dual of this subalgebra is exactly A upper P prime. So it's exactly the parabolic subalgebra for the second parabolic P prime. So for this, one needs to recall that the correspondence on simple modules induced by Koszul self-duality of O sends W to W inverse W0. In particular, it changes left cosets with right cosets. By exactly the same proof as in category O, one shows that the algebra A upper P prime is Koszul. Consequently, both A lower p and A upper p prime are Koszul and Koszul dual to each other. Here is an example. Consider the category O for SL3, in which case the Weil group consists of the elements E, S, T, ST, TS, and W0. Let us choose the parabolic subalgebra such that the corresponding parabolic subgroup consists of E and S. Then the shortest coset representatives of W modulo WP acting on the left are E, T, and TS. So we have seen the corresponding graded projective modules in the parabolic block many times. The projective PE has the simple E on top and S in the socle. The projective PT is also injective. It has T on top and T in the socle, and TS and E in the middle. And the projective PTS is also injective. It has TS on top, TS in the socle, and T in the middle. Here is a description of the algebra of this block by quiver and relations. We have three vertices, TS, T, and E, and the arrows alpha from TS to T, gamma from T to E, delta from E to T, and beta from T to TS. The relations are that gamma after delta is 0, gamma after alpha is 0, and beta after delta is 0. And then here in the middle we have that alpha after beta is equal to delta after gamma. Let us now look at the corresponding singular block. The longest representatives in W modulo WP acting on the right are the elements S, TS, and W0. Let us denote by bold S the translation of LS to the corresponding wall. Then the bold TS is the translation of LTS to the wall, and the bold W0 is a translation of LW0 to the wall. So here are the pictures of the graded projective modules in the singular block. The projective PS is a Verma. It has S in the top, W0 in the socle, and TS in the middle. The projective PTS has a Verma flag of length 2, with delta S as a submodule and delta TS as a quotient. And the projective PW0 has a Verma flag of length 3, with the Verma module delta S as a submodule, the module delta TS in the middle, and the module delta W0 in the top. The description of the algebra of this block by quiver and relations is as follows. We have three vertices, W0, TS, and S, and then the arrows psi from W0 to TS, zeta from TS to S, theta from S to TS, and eta from TS to W0. And the relations are zeta after theta is 0, and psi after eta is equal to theta after zeta. And we have seen already last time that this algebra is Koszul dual to this algebra. Let us now move to Koszul duality of functors. As usual, we denote by K the Koszul duality functor for category O, and we denote by K upper P the parabolic Koszul duality functor. This is a Koszul duality functor from the down arrow category for the singular block to the up arrow category of the parabolic block. Theorem by Steen-Riom-Hansen from 2004. The following diagram commutes up to isomorphism of functors. So we can start from the down arrow category of the singular block, translate out of the wall to get to the down arrow category for the regular block, and then go by Koszul duality to the up arrow category of the regular block. Alternatively, we can start from this down arrow category for the singular block, use the parabolic Koszul duality functor to go to the up arrow category for the parabolic block, and then use the inclusion to go to the up arrow category for the regular block. The claim is that these two ways commute up to isomorphism of functors. Proof. Translation out of the wall realizes the singular algebra inside the centralizer subalgebra of the regular algebra as a part generated by elements of degree 0 and 1. And for linear complexes, this corresponds exactly to the Serre subcategory generated by the corresponding simple modules. And this is exactly the description of the parabolic part of the regular block. So the reference is the paper by Steen from 2004, which is called Koszul duality of translation and Zuckerman functors. We also have the adjoint statement that the following diagram commutes up to isomorphism. We start from the down arrow category in the regular block. We translate to the wall, to the down arrow category of the singular block, and then go by the parabolic singular Koszul duality to the up arrow category of the parabolic block. This is one way. The other way is that we use Koszul duality to go from the down arrow category for the regular block to the up arrow category of the regular block, and then we use a derived Zuckerman functor to end up in the up arrow category for the parabolic block. Proof? This is basically the adjoint diagram for the previous block. We only note that Koszul dualities are equivalences, so for adjunctions I would need to write here k prime in the opposite direction and kp prime in the opposite direction. But since they are equivalences, something which is intertwined by equivalences is intertwined also by the inverses of those equivalences. And another remark is that translation out of the wall is by adjoint to translation onto the wall up to this graded shift by the lengths of the longest element in the parabolic subalgebra. So this follows easily from the computation if one recalls the translation onto the wall sends the dominant verma in the regular block to the dominant verma in the singular block, and the translation out of the wall sends the dominant verma in the singular block to the indecomposable projective which corresponds to the longest element in the parabolic. And the dominant regular verma here in this projective appears exactly with the shift given by the longest element in the parabolic subalgebra. So now we can compose these two Koszul dualities to get the following statement: that the following diagram commutes up to isomorphism. So we go from the down arrow regular category to the up arrow regular category. The first path to go there is that we use the projective functor theta w0p appropriately shifted, and then the Koszul duality. And the other way is that we first use the Koszul duality, and then we use the composition of the derived Zuckerman and inclusion. And that this commutes follows directly by composing the first two diagrams. Of course, we can change the projective functor adjusted by some graded shift simply to the projective functor. This means that we would need to move the graded shift through Koszul duality. Then we would need to change the composition of derived Zuckerman and inclusion by the following things. Then we will have to adjust it by both homological and graded shift. This is because how Koszul duality intertwines with the shift in grading. So it maps it to a composition of both homological and graded shift. In particular, using the fact that the projective functor theta w0p is self-adjoint, it follows that the composition of derived Zuckerman followed by inclusion and then adjusted in this way. So the homological shift minus length of w0p and the graded shift length of w0p, this functor is self-adjoint. Here is an example. Consider SL2, then the while group consists of E and S. So translation of PE through the S wall gives PS, and translation of PS through the S wall gives PS shifted by 1 plus PS shifted by minus 1. And Koszul duality, it maps PE to LS and PS to LE. Projective resolutions of LS and LE are as follows. So LS is covered by PS with the kernel PE shifted by minus 1. LE is covered by PE with the kernel covered by PS shifted by minus 1. And then the kernel is equal to PE shifted by minus 2. Applying the Zuckerman functor to the first complex, we just get here the top of P shifted by minus 1, which is LE shifted by minus 1, but then also shifted by 1 in the homological position. Applying Zuckerman to the second resolution, we get LE here in 0, 0 place, and also LE here in the place minus 2, 2. So we get this module. Now, after the adjustment by 1 and minus 1, so this is the length of S, we get LE in the first case, and LE shifted by 1 and minus 1 plus LE shifted by minus 1 and 1 in the second case. If we recall how Koszul duality interacts with graded shifts, then we see that LE, this is exactly the image of PS. So this LE is exactly the image of this PS. And LE shifted by 1 and minus 1 and by minus 1 and 1. So this is exactly the image of PS shifted by 1 and PS shifted by minus 1. This is the illustration of the commutativity of that diagram. Now we can discuss Koszul duality of shuffling and coshuffling functors. Let us fix a simple reflection S. Then we have the corresponding shuffling functor Cs defined as a cokernel of the unique up to non-zero scalar natural transformation from the identity shifted by minus 1 to theta s. And we also have the corresponding twisting functor Ts defined in a Lie-theoretic way using some localizations and so on. What we know about it is that there is a natural transformation from Ts to the identity shifted by 1, which is non-zero when evaluated at the dominant Fermat module delta E. Theorem by Sergei Ovseyenko, Katarina Stropel, and myself. The following diagram commutes up to isomorphism of functors. So we go from the down arrow regular category to the up arrow regular category, and one way is derived shuffling followed by Koszul duality, and the other way is Koszul duality followed by derived twisting. In other words, the shuffling and twisting are connected by conjugation with Koszul duality. And note there are no graded shifts explicitly written in the picture, but this is a graded picture with all functors graded. So here is a sketch of the proof. First of all, we observe that the composition of the left-derived Zuckerman with inclusion and then adjusted by 2 in degree and by minus 2 in the homological position is isomorphic to the composition of the right-derived Zuckerman with inclusion. So this follows directly from the self-adjointness of the composition of left-derived Zuckerman followed by inclusion, and then adjusted by the length of S, which is 1. Then we know that on projective modules we have the following short exact sequence of functors. Ts is a subfunctor of the identity shifted by 1, and the quotient is the composition of the Zuckerman followed by inclusion and then shifted by 1. So using this lemma above, we can extend this to a triangle of functors. So Is and then Lzs shifted by 1 in degree and minus 1 in the homological position maps to the left-derived twisting. This maps to the identity functor shifted by 1, and this maps to the composition of Lzs and then Is shifted by 1. Conjugating this triangle by Koszul duality gives the following triangle. So the Zuckerman conjugating by Koszul duality gives us translation. Then we have the conjugation of twisting by Koszul duality. Identity, of course, conjugates to itself. It's just we have to adjust the degree shift to both degree and homological shift because of how Koszul duality intertwines with degree shift. And here is the same. The Zuckerman is Koszul dual to translations through the wall. Now we can rotate these triangles twice to the right, and we have this triangle of functors. And from this triangle of functors, we readily see that the conjugation of twisting by Koszul duality is the cokernel of the unique natural transformation from theta e shifted by minus 1 to theta s. So this proves Koszul duality of shuffling and twisting functors. Here is an example. Again, we take SL2 and W is equal to E and S. The shuffling of PE is LS, and the shuffling of PS is PS shifted by 1 in degree. So Koszul duality maps PE to LS and PS to LE. So let's compute the twisting of these modules. So we have already seen the projective resolutions of Ls and Le previously. So applying the twisting functor to these projective resolutions gives the following. So the twisting functor just moves Ps, it shifts it by 1 and maps Pe to Ls. So the outcome will be just the injective module IE. And in the second resolution, so P goes to Ls, Ps is shifted by 1, P goes to Ls. So we have homology in homological position -1, which is Le, so we will get Le shifted by 1 and -1. We know that injective, this is exactly the image of the simple Ls under Koszul duality, so this matches. And then again, if we recall how Koszul duality interacts with gradient shifts, we get that Le shifted by 1 and -1 is exactly the image of Ps shifted by 1 under the Koszul duality. So this matches as well. Let us now discuss the category of linear complexes of tilting modules. So LCT is the category of linear complexes of tilting modules in O. So the twisting by the longest element in W is an equivalence from the category of linear complexes of projective modules to the category of linear complexes of tilting modules. We know that all tilting resolutions of dual Verma modules are linear, and all tilting co-resolutions of Verma modules are linear. And combining the Ringel and Koszul cell dualities of O, we have that the bounding part of the category of linear complexes of tilting modules is equivalent to the graded version of O. Proposition: Koszul cell duality of O0 sends Verma modules to dual Verma modules. Proof: Koszul duality sends delta E to LW0, this we know, and it intertwines shuffling and twisting. Applying shuffling to delta E produces all Verma modules. Applying twisting to LW0 produces all dual Verma modules. So hence K sends Verma modules to dual Verma modules. In other words, linear projective resolutions of Verma modules are costandard objects in the category of linear complexes of projective modules. So the bounded version of that category is a graded version of O. So it's a category of graded modules over graded quasi-hereditary algebras. It has costandard objects. And these costandard objects are exactly the projective resolutions of Verma modules. Applying the twisting with respect to the longest element, we get that the linear tilting resolutions of dual Verma modules are costandard objects in the category of linear complexes of tilting modules. Applying duality, we get that the linear tilting co-resolutions of Verma modules are standard objects in the category of linear complexes of tilting modules. Note that if we do the Ringel-Koszul duality, so the Koszul duality matches W with W inverse W0, and the Ringel duality matches X with W0X. So the Ringel-Koszul duality matches delta W with delta W0 W inverse W0 for any W in the Weil group. The question which I want to ask is what are the indecomposable tilting objects in the category of linear complexes of tilting modules? Recall that each tilting module has a Verma filtration and a dual Verma filtration. For the tilting module TW, the Verma filtration starts with delta W, and all other standard modules which appear in the Verma filtration of TW appear with strictly positive shifts in gradient. This is because of the positive gradient on O, and that the Ringel duality preserves this positive gradient. So similarly, any costandard filtration of TW ends with nabla W, and all other costandard modules appearing in this costandard filtration appear with strictly negative shifts in gradient. This has the following consequence: corollary. The non-zero homology of an indecomposable tilting object in LCT is concentrated in homological position 0 and in degree 0. Proof: standard objects are co-resolutions of Verma modules, and hence they have homology below or on the diagonal. So the Verma module, it lives on the diagonal or below. Therefore, if we take an indecomposable tilting objects in the category of linear complexes of tilting modules, so it's constructed from standard objects, and in this standard filtration, all objects appear with certain types of graded shifts. So it follows that the homology of an indecomposable tilting object should be below or on the diagonal or in a non-positive homological position. At the same time, looking at the co-standard filtration, we have the dual version that the homology of an indecomposable tilting module should be above or on the diagonal and in a non-negative homological position. So combining these two things together, we get our corollary. This has the following consequence. Each simple object in O0 is isomorphic to a complex in the category of linear complexes of tilting modules. Moreover, each such complex is an indecomposable tilting object in this category. So this is because of the positivity of the grading and the fact that tilting objects have homology in position 0 and degree 0, so it should be semi-simple. And then simply by additivity, it means that for an indecomposable tilting object, the homology should be simple. And then comparing the numbers, we have this corollary. Another way to phrase this corollary is that the Ringel-Koszul self-duality of O matches the simple module LW with the indecomposable tilting module T, W0, W inverse W0 for any W. And the reference for this is my paper from 2009, Applications of the Category of Linear Complexes of Tilting Modules Associated with Category O. The last result can be generalized in the following way. Claim: for any pair x and y of elements in W, the module theta x Ly is isomorphic to some linear complex of tilting modules. Moreover, the Ringel-Koszul duality of O matches this linear complex with the module theta y inverse W0 applied to L W0x inverse. Here is a rough idea of the proof. We do induction on the lengths of x. The case length of x is equal to 0 is exactly the previous result. In the induction step, we start from theta x Ly, which we assume is represented by a linear complex of tilting modules, and we apply the translation theta s such that xs is greater than x. So using Koszul duality of translation and Zuckerman functors, one can show that the outcome, which will no longer be a linear complex of tilting modules, but it will have tilting modules on the diagonal, just above the diagonals, and just below the diagonals. So, but one can show that the contributions just above the diagonals and just below the diagonals, these contributions can be killed using the homotopy. This is proved in my paper Some Homological Properties of Category O2 from 2010. Here is an example. In the SL2 case, when the Weil group consists of E and S, we have that the tilting module Ts is equal to Ls, and hence the linear complex of tilting modules representing Ls is just a trivial complex where Ts is in the homological position 0. The linear complex representing Le is the following complex. We have Te in homological position 0, so it surjects on Ts shifted by 1, and Ts shifted by -1 is in the socle of this module. So the middle part is exactly Le. So here is how it looks if we draw these modules in their graded version. So Te has S in the top, E in the middle, and S in the socle. So the top S goes to Ts shifted by 1, and the socle S comes from Ts shifted by -1. So the homology is exactly here, Le in the middle. And also we have the translated simple theta S Ls, which is just Te, and it is again represented by the trivial complex 0 goes to TE, goes to 0. Finally, some questions for PhD students. Question 1. Check with all the details that the image of the algebra homomorphism from the singular block to EAE, given by translating out of the wall, coincides with the subalgebra of EAE generated by degrees 0 and 1. So here one needs really to use positivity of the grading. Question 2. Prove with all details that the algebra of the principal parabolic block is Koszul. Question 3. Compute with all details the graded by adjoint to translation onto the wall. Question 4. Prove that for a fixed simple reflection, the corresponding coshuffling is Koszul dual to Enright's completion. Question 5. Compute the linear complexes of tilting modules representing the simple modules in the principal block of category O for SL3. Thank you very much and see you next time.